Today, we are going to talk about a fundamental rule of the universe, something we usually just call chaos. But what if I told you that scientists are now taking that chaos and using it to build revolutionary materials, stuff that could power missions to other planets? Well, to get how that's even possible, we have to start with a question that sounds incredibly simple. So yeah, why does an ice cube, when you leave it out on the counter, turn into a puddle of water? It seems obvious, right? I mean, it just gets warmer. But the real why behind it, well, that's a lot deeper and a lot more interesting. And here's the kicker. Why does it only go one way? Why doesn't that puddle of water ever just decide to suck all the heat out of itself, push it into the room, and freeze back into a perfect ice cube? The fact that it doesn't, that this is a one-way street, that points to some powerful, fundamental law of the universe at work. To figure out that law, we need to crack open the universe's rulebook. There's a whole field of science for this. It's called thermodynamics. It's basically the set of rules that governs energy and explains why materials change from one state to another. Okay, so first rule you gotta know is about something called internal energy. Just think of it as all the energy that's packed inside a system, like our ice cube. You can add heat to it, or you could, say, smash it with a hammer, and its internal energy changes. It's the first key piece of our puzzle. But for something just sitting on a countertop, scientists like to use a slightly different measure called enthalpy. It's a bit more practical. It accounts for the heat you add, plus the tiny bit of work the system does just by existing. For what we're talking about, you can pretty much just think of it as the total heat content. And this, right here, is where it starts to get weird. Because when you actually measure what's happening when something melts, you hit a major puzzle. It seems to fly in the face of a simple rule we see everywhere else in nature, that things always want to go to the lowest possible energy state. Now, we don't have to guess about any of this. Scientists have these amazing tools like the differential scanning calorimeter, or DSC, that can measure these energy changes with incredible precision. It basically just tracks exactly how much heat a little sample absorbs or gives off as you heat it out. And this is what the machine shows us. Look at step 2, crystallization. When the atoms snap into a nice, neat, ordered crystal, they actually release heat. They're settling down, moving to a lower, happier energy state. But then, look at step 3, melting. To break that perfect crystal apart, the material has to suck in a ton of heat. It has to absorb energy. So that brings us to the big central question. Melting happens all by itself, right? It's spontaneous. But to do it, the material has to actively absorb energy, increasing its own enthalpy. It's like watching a ball spontaneously decide to roll uphill. Why on earth would the universe let that happen? What are we missing here? Well, the missing piece. It's a concept that is famously misunderstood, but it is, without a doubt, the secret driving force behind almost everything that happens in the universe. And that concept is entropy. You've probably heard entropy called disorder or randomness, and that's not wrong, but it's a little too simple. A much, much better way to think about it is as a measure of possibilities. It's the total number of different ways you can arrange all the little bits and pieces of a system. The more possible arrangements there are, the higher the entropy. Let's go back to our ice tube. When it's a solid crystal, all the water molecules are locked into this neat repeating pattern. There are very few ways you can arrange them. That's low entropy. But as a liquid, those same molecules are free to tumble around, point in any direction, and swap places. There are just countless possible ways to arrange them. That's a high entropy state. And the universe just finds that state way, way more probable. And when I say more probable, the numbers are just mind-bending. I mean, look at this. If you take just 100 atoms of one type and mix them into 100,000 of another, the number of possible ways you can arrange them is that. That's a 1 with 342 zeros after it. It's not just likely to mix, it's practically inevitable. The universe has an incredibly powerful drive to explore all those possibilities. So this is where it all comes together, in the free energy equation. For anything to happen spontaneously, like our ice melting, the overall free energy, which we call G, has to go down. Now, we already saw that the enthalpy, H, goes up when ice melts, which that's not helping. But look at that other part, T times S. T is just the temperature, but S, that's our massive, enormous increase in entropy, in possibilities. As the temperature goes up, that TS term becomes huge and negative, and it completely overwhelms the increase in enthalpy. It drags the total free energy down. And that is why ice melts. It's the universe's unstoppable preference for possibility. So, for a long time, this was just this really cool piece of fundamental science. It explains why things happen. But recently, engineers started asking a pretty radical new question, and they've started turning this whole concept into a powerful new tool for designing materials we've never been able to make before. And the question is this: what if, instead of just letting entropy happen, we design materials from the very beginning to have the absolute maximum possible chaos, the highest possible number of arrangements? This is the whole idea behind a wild new class of materials called high-entropy alloys. And the logic is pretty simple. An old-school alloy with maybe two main elements has a certain amount of entropy. But look what happens when you decide to just throw 5 different elements together in equal amounts. The number of ways you can arrange those atoms just skyrockets. The entropy more than doubles. And that powerful drive for chaos can actually force these atoms into a surprisingly simple, stable structure, even when you're mixing elements that would normally never get along. And this is leading to some amazing breakthroughs. Take the generators that power deep space satellites. For those to work, you need a material that is, 1, a terrible conductor of heat, so one side stays hot and the other stays cold, but 2, you also need it to be a fantastic generator of electricity from that heat difference. The problem has always been that materials that are good at one of those things are usually awful at the other. The answer was to design with chaos. Scientists came up with a new ceramic, but instead of having just 1 or 2 types of atoms in the crystal, they put 5. This huge, random mess of different-sized atoms creates chaos on the atomic scale, acting like a forest of roadblocks for heat trying to get through. It completely disrupts the flow. And the result? It's just astounding. This high-entropy ceramic does both things at once. It has an exceptionally low thermal conductivity because of all that atomic chaos, but it also has a really high Seebeck coefficient, so it generates electricity super efficiently. It completely shatters that old trade-off. So it all boils down to this really new, powerful idea. By cranking up the entropy on purpose, by maximizing the chaos, we can make these incredibly stable, incredibly useful new materials. We're taking the universe's preference for possibility and turning it into our own design principle. Which, of course, leaves us with one last really exciting question. Now that we're learning how to design with the universe's hidden driver instead of against it, what other huge challenges can we solve? If we truly learn to embrace chaos, what other impossible materials are suddenly within our reach?